So this is Colin, who's one of our star section leaders. Is anybody Colin's in Colin's section?
Tragic.
Tragic. So, you get the benefit of his knowledge tonight. He's going to do a little review, and you guys have the floor, so you can ask as many questions as you want. I will turn it over to you.
Thanks. Okay, awesome. So as Chris mentioned, my name is Colin. For those of you who are just now putting a face to the name that's on all the section handouts. So also, as Chris was saying, the goal of tonight is really to help you all prepare for the midterm in whatever way you think will be the most helpful to you. So I have some slides prepared that essentially go through a quick little rundown of all of the important topics that you've covered so far. You are more than welcome to stop me at any point if you have questions about things I'm presenting, or if you say just hey, we should focus on something else because this would be that would be more helpful to me than what we're doing. Yeah, anything really quickly before we begin just going through this? Awesome, cool. So, starting off, Big O, this is one of the first things you saw in the class. This is just sort of a measure of the efficiency of things that you're looking at, programs, algorithms more generally. And so the main points I wanted to hit on here are that when you're doing Big O analysis, saying this is O of n or something like that, you want to ignore coefficients. So if you say 3n, it's actually just n, and constants, so if it's 3n plus 5, it's still just n. If you're asked to analyze the Big O efficiency of some chunk of code that you see, the most common thing that you'll have to do is look at some loop and say, how many times this run? And that's usually in terms of n or some factor of n. And then also make sure that you're looking at the worst case running of that loop, because sometimes it can run fewer times than n in a good case, but make sure you're accounting for what could really happen in the worst case. And when you have a loop, you multiply the number of times that loop happens by the complexity of whatever is inside, whether that's some operation with a data structure or another loop or whatever else you want to do. The last thing I wanted to really talk about was recursion. I think that the most Big O practice in this class happened at the beginning when you were just looking at loops and a little bit of the data structures, but you've seen recursion since then. And so I encourage you to do some practice problems that also involve recursion with Big O or Big O with recursion. And the trick there is really just look at the recursive trees, or just think about how many times the recursive function can be called. And that's the equivalent of how many times a loop runs. And I think you should be able to find some practice problems with that on old midterms, if nothing else. Any questions? Cool. Okay, ADTs. This one I wanted to spend not as much time on because you've used ADTs a lot in the assignments. Just a quick recap of a lot of things you've seen so far. Vectors are equivalent to array lists. If you took 1-6a here, you just add elements in, you can insert them, you can delete them, access things at certain spots, stuff like that, get the size. Grids, sort of like a 2D array, you can look at things in a specific row and column and change things and resize them if you want to and stuff like that. Also really handy for the inbounds method that we provide. Stacks you saw as this last in, first out thing where you're sort of piling data into a stack, and then if you ever want to access data in it, you have to pop it off the top. Queue is in some ways the opposite of that. You put data in to the queue, and then whenever you want to take stuff out of the queue, you have to take it from the very front. So the first thing that was enqueued was the last thing or the first thing that you take out. Sets, you just have these elements that you put in there, and you know that each element in there is only in there one time. So the important operations that you'll be doing are seeing if an element is in the set and iterating over a set, perhaps. And finally, a map. You have a key, which can be one data type, and then you look up the key in the map to get some value, which can be another data type. Either the key or the value or both can be itself a data structure. You can, for instance, have a string that's a key, or key that's a string, and a value that's a vector, or any other permutation of the data structures you want. And those are all valid things to do. Lots and lots of other data structures out there. I would definitely encourage you to check some of them out. They're really cool. There's a whole class on them here that was one of my favorite classes here. Rich area for exploration. Just one little tip on data structures that came up a lot in the assignments and could come up on the exam. Just make sure that you're never going out of bounds when you have a data structure. Those are the things that'll give you these like little runtime errors where you're running a program and then some red thing comes up saying you went index out of bounds on a grid or a vector or other things. Make sure that you avoid that pitfall. Any other questions about data structures? Awesome. And you remember you can come back to anything at any point. Sorting. So I believe this was mostly just covered in one lecture, but also an important topic because it comes up a lot in computer science in general. It's a very common problem that people try to solve. You looked at insertion sort, selection sort, merge sort, and quick sort. There are, once again, many more sorting algorithms that exist for specific types of data sets. The problem, of course, is that you often don't know what type of data set you're working with, so you can't know ahead of time like what sort will be the best. Some applications in the real world will try to optimize based on what kind of data they think they'll have. But all that to say, we have all these different sorts because different sorting algorithms work better for different sets of data. And that's what I'm talking about with properties of data you're sorting. Also, another reason that we have these different sorts is that there's a trade-off between the space you use. So sometimes you'll have to like allocate an extra array if you're sorting an array in order to do the sort. And sometimes you'll have to, you won't care as much about the space that you allocate, but you will care about how long it takes. And that's really often the challenge with sorting, like making sure it runs quickly. Other questions about sorting? Cool. And I would recommend that, if nothing else, you just like remind yourself of how the analysis of the big O for the sorting algorithms works, because that's something that we care about a lot, as I was mentioning. Like, you care about efficiency, so you care about how do we analyze that efficiency. Good. Okay, getting into the more recent stuff. You've been talking about recursion. And so we talk about recursion as a way to break a big problem up into more manageable chunks that you can eventually solve in a more easy way. And so when you talk about recursion, you have your base case or base cases that are the simplest possible input that you can operate on with your recursive function. And usually the way that you handle the base case once you reach it is some relatively simple operation that can return some result to the function that called it. We call that the caller function. Then in order to reach the base case from the original input, you have your recursive step. That involves reducing the problem to the base case. And so you've seen in some of your programs there might be multiple recursive steps that you call within one function. But the idea is always just like you're making one or more recursive calls in the recursive step, and then maybe like working with the return value of the recursive call, or just maybe returning it directly to the caller function. But in that way, you're eventually able to solve the whole problem by just calling the recursive step until you reach the base case. We also talked about wrapper functions and helper functions. We sort of talk about that in this class as just a way to introduce more parameters if you want more parameters. From a real world perspective, the point of this is that sometimes you want some person in coding a different thing to be able to call a recursive function. And they don't want to know exactly what parameters you need in order to make the recursive function work. They just want to know, like in the lecture, you had this permute example. And a user of the recursive function just wants to know what all the permutations of that word or that string is. And they don't want to know, like, oh, well, I need the word I'm building up and the word that I've seen so far in order to do the recursion. Other things, we're going to talk about backtracking in one sec, but anything more generally about recursion? I can also slow down. I'm realizing that I'm talking really quickly, but that's just me also. Awesome. Also, just so you know, these slides I'm going to either email out or post on Piazza afterward. So just feel free to write down whatever you think will be helpful to you. Cool. So often we see recursion done in a couple of ways. We talk about exhaustive recursion as this style of recursion that tries like lots of different possible combinations, by which I mean every possible combination of the input. And so I was talking just now about the permute example from lecture. We wanted to print out every single way that you can order the letters, and that ends up being like a lot of different recursive calls to reach that, but eventually you've tried every different possible combination. And there are times when a problem will require that you exhaust all the possibilities that way. As I mentioned, though, that's a lot of different calls, and so sometimes you want to see if you can short circuit that a little bit. And that is part of where recursive backtracking comes in. So the thing we talk about with backtracking is this like little thing you can remember: choose, explore, unchoose. And what that means is if you have multiple ways to proceed with recursive functions in the recursive step, or recursive case, I should mention, then you want to try one option, and that could be choosing one letter to try in some string manipulation, or in the maze you saw in lecture, choosing one direction to try, and then explore, meaning you go into that recursive function and see maybe can I finish the program just going down this path, or do I get the best option going down this path? And then once that all returns, meaning that that choice has like, you've gotten the result you want given that choice, then you get that back in the recursive caller function, and then maybe you just return immediately, maybe you keep it around to compare to other things, and then you unchoose, which could mean like removing something from a data structure if you're like adding moves into a vector of moves that you've made, or perhaps adding something back in to a vector if you were removing it as the choosing. But ultimately, it's similar to exhaustive recursion in that you're probably looping and you're making every possible choice until you get the answer you want. So that was a whirlwind of these very complicated recursive strategies that you see a lot in, you saw in parts assignments 3 and 4. So I'm going to let that digest for a little bit, and please, please, please ask questions. One thing I should mention also, just applying to recursion broadly, is that you've talked about this concept of arm's length recursion, or at least maybe heard the term once. This is the idea that you're sort of like reaching your arm into a recursive function and trying to see ahead of time whether it will reach the base case. And this is a strategy that we try not to do, if at all possible, because you want to, as much as possible, depend on your base case to tell you when the recursion should end. So an example of this is if you're doing a string manipulation recursion problem, and you want your base case to be like, well, if the string's empty, if some string in the recursive call is empty, then you end, because that's the simplest case. But then in your recursive step, you're saying, well, if the string's length is 1, then will this come back exact? Oh, perfect. Cool. Sometimes you'll see this type of thing where the recursive step has this check: if the string's length is 1, then like return it immediately, or something like that. And you want to avoid that because A, it's kind of bug prone, and B, it's not as clean. The recursion should end when like there is really no more work to be done, and it is as simple as possible. There are like lots of other reasons, but trust that if you find yourself having to like do a lot of if checks on the recursive step, there may be some way to incorporate that into the base case so that it just like involves less work on your part. Not to say that you always do this. You saw in Sierpinski triangle, and perhaps there's another drawing recursive function where you did need to like cut off at order 1. So don't be like, don't be super scared of that, but like try. Last questions about recursion? Cool. We are ripping through this, so We might get to do some practice problems from the old exams, but I wanted to make sure this is all out there first. Okay, classes. So for those of you who took 106A here or did pass like formal programming, you've almost definitely seen classes. If not, this could be new to you. So the basic idea is that you have objects. And you've seen these before. A vector is an object, a grid is an object, and they have classes that define how they work. So I use these scare quotes here when I say that objects encapsulate data and provide interfaces and that abstract away details. I use these scare quotes because these are words that made no sense to me before I took CS here. So what I mean by all this is that in vector, for instance, which is a class, you have this interface of different methods that you can call on a vector, such as contains and insert and remove and size and clear and all these things. But you never had to think about how those work until relatively recently when you were implementing the vector class. You just had to know that if I want to clear everything in a vector, I can call .clear. And that's an important idea in computer science, the idea of abstracting away the details and just saying, in the abstract, I just know that I have a method that does this. And so that's the basic premise of classes. They have these instance variables or members. They have data inside of them that describe the state of the object. So in vector, that means like what its size is, what elements it has, and stuff like that. That the user, I should say client, that's a more technical word, but like anyone using this class doesn't have to know exactly about. They just have to know that they can access them or change them through the methods in the interface. That all make sense? So as I mentioned, they have classes will generally have some or all of these things. Member variables, instance variables, or fields, which are, as I was saying, size and whatever internal way you're storing all the data looks like. Member functions or methods, so those are your getters and setters, like getX and setX for a point, as well as contains, clear, and all those things. Constructor and destructor. Constructors you'll almost always see. Those are when you say like, you have a grid constructor that has the number of rows, number of columns. That's just a way of you being able to put information about the object in as you're creating it. Destructors are things that you might not have seen until recently. Those are, like, they're not functions exactly, but they work on an object when it goes out of scope or when you're deleting it. And that takes care of any memory management. So a little bit, we're going to talk about pointers, but the point of a destructor is to free memory that this object has allocated. That all kind of makes sense. We're going to talk about pointers in a sec, but can address anything now. Cool. And then finally, just wanted to mention, in case you see this in code, there's this keyword this, and you'll see it as in this arrow something. And the arrow refers to, again, pointer syntax. We'll talk about that. But if you see this arrow something in a class, that means it's referring to a member of the class, which could be either a member variable or a member function. I think, as far as I'm aware, you probably don't need to use this if you're writing something yourself, but it can be really helpful, and there may be times with, like, contrived cases of multiple variables called the same thing where you might need to know it. Good? Okay. Pointers. This is a pretty sparse slide because I really want to encourage you to ask questions on this one. I'm not sure exactly what will be the most deserving of explanation here, but the basic idea of a pointer is that it is a variable that stores where something is in memory. Let that sink for a sec. So we talk about dereferencing pointers, meaning if you dereference a pointer, you go into that spot in memory that the pointer has as its value and get whatever is at that spot in memory. Conversely, you have referencing, which is, you've seen this like ampersand, the little, I'll I'll probably write some code on here to do a little example, I think. But you can get the memory address of a variable using the referencing. Pointers can point to any memory address, meaning that you can have a pointer point to something on the stack, which is like most things you've seen so far. Like if you say like int x equals 7 in a method, like that's on the stack for that method. Also, there's this thing called the heap, which is dynamically allocated memory that you have to clean up yourself using delete. And you know things are on the heap if they involve the word new when they, I'm sorry, I'm gonna just turn my phone off. If you had the word new when you declared some variable, you know that its memory is on the heap. And so that pointer is pointing to an address on the heap rather than the stack. And there's no special distinction between, like if you have some int pointer, there's no stipulation that it always point to something on the stack versus the heap. It can change at any time, but it can point to any memory address. Okay, so you've seen pointers more recently than most other things. And so do you think it would be helpful for me to just go through a few like things on the whiteboard about how pointers work? Okay, I'm definitely seeing some nods, which I appreciate. So sorry, Chris, would you mind just pointing the camera over to the whiteboard? Or I can do it on the computer if you think that'd be more helpful. Cool. Yikes, I don't have my marker, but there are markers here, which is great. I just found them. Okay. Okay, this is going to be great exam practice because I'm doing this on the fly, and so I might make mistakes, and then you should correct them. Awesome. Okay. Marker number 1 down. Number 2, nice. Okay. Okay. So I'm starting off with this variable. It's on the stack, nothing different from what you've seen so far. So now, when the pointers come in, is I have this asterisk, this star, meaning this variable is a pointer. Then you say int star, you can say ptr, and then equals, and then I guess I can make this a little more interactive since we have time. How do you get the memory address of this x? Ampersand, great. That's what I was talking about with the referencing. So now we have int star pointer, int star ptr, I'm sorry, I should clarify that, is the reference of x. So what kind of numbers might we see if we were to say like print out ptr right now? Hexadecimal? Awesome, great. So I'm going to say in a little comment here, int x equals 1, but x is stored at, I'm going to choose some memory address. I'm going to say 0x1000. And so this 0x means it's a hexadecimal value. And this just happens to be a memory address where we're saying the int might be stored. And what section of memory is this address at? Stack, awesome. So if we're in, oh, that's fine. If we're in some method, assume we're in just like some function, I suppose, where I declared x, then it's declared on the stack, and I'm saying it's at this memory address. So what do we know about PTR right now? Actually, better way of framing this. This marker is dying. I might want to replace it just so it shows up in the video. C out, oh, it's fine. C out PTR. What does this print?
0x1000.
Awesome. So PTR itself is 0x1000, some number of zeros. And how do I use the fact that it's referencing a specific integer on the stack as well? How do I get its value? Dereference it, exactly. So if we want to get the value, how do I dereference it? Exactly. So dereference pointer, or PTR, and this is 1. Awesome. Now, let's get a little trickier. How do I get some dynamically allocated memory, meaning memory on the heap? Heard a word? New. Awesome. So we'll stick with ints for this example. So starting off, any pointer has this int star. And it can get really confusing, at least for me, that there are like all these stars floating around. There's like dereferencing has a star, and then pointers themselves in their declarations have stars. So just think like anytime you see a star around a variable, if there's a type there as well, you can just sort of like in your mind have these little parentheses and say like, this is a pointer type. And I think this will help you out a little bit when you're doing the mystery problems or the stack trace problems in the practice midterms and stuff. There's a lot of like weirdness with pointers to pointers and pointers by reference and stuff. And the way to try to undo those mental gymnastics around pointers is just like if you have like a double star or an int star, just like in your mind sort of put those together and say like this is a pointer. All good? Okay, so we were saying that we wanted to do something on the heap. So we can say int star, I'm going to say heap ptr equals, and you mentioned how I do this, the word new. So int star heap ptr equals new int. Okay. Now, what happens if I dereference this? Seeing a shaking head. Get an error. Is that what happens? Shaking heads again. What's going on here? Perfect. No one give me a great answer because there is no great answer. This is stuff that you don't want to do. You've allocated some memory on the heap here. So this pointer, actually I should say, what is the value of heap pointer itself right now? Just like give an example of what it might be. What type is this heap pointer? It's an int pointer. And so for a pointer in general, what type of value will you see if you look at it? Memory address. Awesome. So I'm going to say this might be like OX 5000. But if we tried to reference it, junk. We have no idea what's going to be there. We have no guarantees. Good? So I'm going to say bad. Always initialize. Can I spell? Yes. Okay. So I'm going to comment this out because I don't want to leave bad code up as if it's something you should do. So how do we make use of this heap pointer then in order to have it be useful to us and not going to like get us junk? Sorry, what? Initialize it. How do we initialize it? Awesome. So the key here is now we have the star heap pointer equals, what number do you want since you gave us 21? Awesome. So we now have seen two ways that dereferencing can work. If we want to access whatever is at the pointer's memory address, then we dereference it to get that. We can also use it to set whatever is at the memory address. That all clear? Okay. Now, I'm going to, let's see, what time is it? Do I want to move on or keep doing this? More? I'm seeing not as much enthusiasm as I got when I originally was talking about let's do pointer examples. So I might move to back to the slideshow, and then if we have time, I'm gonna move through one of the one of the mystery problems that uses a lot of pointers because they get like really tricky, in my humble opinion.
Maybe if you have time, maybe one of the recursion ones, but I don't want to make you do it off the top of your head if you haven't prepared it.
Well, I proofread all of them, so I think we'll be fine. Cool. Okay, and could we move the camera back to? Thanks. All right, and I just also want to say as a word of warning or encouragement, depending on how you interpret this, pointers are really tricky, and they are also really important. So if you find yourself like working through the mystery problems and seeing these like pointers to pointers and passing a pointer by reference, and you think like, wow, I don't really understand what's going on here, it's really confusing, I would say don't worry about that too much, but also don't dismiss it as something that you'll never have to know. Just accept that like you will use pointers a lot in the rest of this class and in further classes if you take any, and it will become really clear. But for now, I think the kind of stuff we were doing up on that board is the most important thing you'll need to know about pointers for now. Cool? Okay. So the immediate application that you're seeing with pointers in this class is in linked lists. And so there are lots of different types of linked lists that you saw on the section problems this past week. They had like linked lists of doubles, of ints, of characters, of strings perhaps, which is just to say that a linked list is a data structure just like a vector. And it's similar, it's worth thinking about like when you'd want to use some of these data structures over others. Linked lists are probably the most conceptually similar to vectors in that they have this sort of like linear arrangement of the data, but you use them in pretty different ways. So if you have a linked list just that you're using, you often have it referred to by its front pointer or its head pointer, which is a pointer to the first element. Sometimes you also see a tail if you have a doubly linked list, which I'll talk about in a second. But that just refers if it's a front pointer to the first element, and then you can traverse it from there by going through its next pointers. And there are a bunch of examples of this, including what Chris just posted on Piazza. But there are some pretty standard idioms, by which I mean like ways that people traverse linked lists and work with linked lists. You'll often want to like have some cur pointer that, or a cur list node that you update by like setting it to its own next list node, stuff like that. And list nodes, just to clarify, contain the data that you want to be working with. So like each node has some element of data, like as if you had some index in a vector, as well as a pointer to the next element, the next list node in the list. And if you have a doubly linked list, which is helpful for a lot of for efficiency reasons, although there are times when we wouldn't want to use it. Then you have a previous pointer as well, so you can go back and forth in the linked list. Just another little implementation tip. When you're working with linked lists, sometimes you will want to think about, is the first element going to be a special case? Is the last element going to be a special case? Or can I use exactly the same code for every element of the list? And my recommendation is think about that really hard. Don't introduce special cases if you don't have to, but there will be times when you have to. Yeah?
What do you mean by
Yeah. So does someone have an example of that you can think of from a recent problem? Otherwise, I can.
Why don't you pull up the Piazza code?
Yeah, awesome. I can do that. Oh, and I am gonna not. Oh, this is up there. Ah! Sorry. No, this. Okay, I think that was fine. Cool. And how am I going to?
You can actually, that little triangle on the top left over there, down a little bit, left, going left.
This is MM.
Up. There you go.
Wow, nice. This is almost, oh, it's good enough for the code. Okay. So here we see, for those of you who haven't seen this Piazza post yet, this is going through a linked list to remove an element that has as its data the string name. And so I'll leave you to look through, or actually, do you want to just like talk through how this code works right now, or have like figured it out by yourselves? I can just point out the one special case.
It's a good one where you actually draw a couple.
Yeah, for sure.
I can move the back.
Okay. Wow, and I can even.
Let's see. Also move the screen up there, the board behind it.
Oh yeah,
See if that helps.
good call. And I'll grab the markers. I'd say probably put it all the way up, and then I can. Oh wait, but there are these things in the middle.
There's that, but maybe if you, what if we left it like right about there, and then you write in the bottom?
All right, I'll try it.
Maybe do that. Is that, I don't know, is that like that little space?
We'll try it out.
You got a room for 3 or 4.
Yeah. Okay. So I'm gonna do what this class has been doing a lot, which is, oh, this is really, okay.
It's not gonna work, don't worry about it.
If I write this, can anyone see that at all? Okay, cool. So I'll try to write a little bit bigger. So this is going to be a list of strings because we're looking for one name. So we've been using all the section leaders in lecture and stuff, the names. So we'll start with Chris. And then next pointer will go to Aaron. Goes to Colin. And which lucky section leader will I pick as my last person? Who likes their section leader the best? Jason. Oh, nice. Jason. He'll be so happy to hear that. Okay. I'm going to do a little slash there to say that next pointer is null. All set? Okay. So we are going to, yeah, sorry, is there a question? Okay. So we're going to start off using this method for removing a name from a list, passing in the name Colin. So when you start out, you have this prev pointer, and it's a node star, similar to that, except it points to a memory address of a node rather than an int. So you have prev is null, and cur, where is that pointing right now? Actually, in the interest of time, I'm just going to do this. That good? Okay. So cur right now goes up here to Chris because it's the front of the list. Then while cur isn't null, cur is not null right now, so you go in there. Value is not equal to Colin, so trust me when I say that these lines say we set prev equal to cur. So actually, when you're doing your own traces, you should never erase, is what I recommend. So I'm going to cross out null, and then have this point to Chris.
Sorry.
Yep. Awesome. And then the last line is cur goes to cur's next. So I sort of, it'd be great if I had another color. Does this work? Yeah. Okay. So cross out this arrow. Cur now goes to Aaron.
Oops. Sorry, I'm not paying attention to the fact there's no white down there now.
Oh yeah.
This is not going to come out on the camera.
Yeah, probably. Okay. So when we get set cur equal to cur next, it goes to Aaron. Then same thing happens. We go up to the top of the loop. It's not, cur is not null, but then what we're pointing to is not the name we want. And when we're looking at how to find the piece of data we want, so like the name, we have to look at cur's value field. Just remember it has the value field and the next field and like maybe other things. But so update everything again. Prev no longer goes to Chris, but now it goes to Aaron as well. And cur now goes to Colin. We get up here, cur is not null, but cur's value is name. So we go in here. Prev isn't null, so we have to go here. And now we set prev, which is Aaron, dot next. And I say dot to stand in for the arrow because like it's kind of conceptually similar. When you look at structs, you'll see that like use a dot when you're not looking at pointers and an arrow when you're looking at pointers. If I say that very cryptically, does that make sense based on things you've seen outside of this session? Great. Okay. So when we have found, when cur is pointing to whatever we want to remove, we set prev, which is Aaron's next pointer, to go, oh, that's not great. Now goes to Jason. And then we delete Colin entirely. Yeah?
This done needs to be declared when we say node pointer current is equal to front is front already declared.
Yeah, great question. So this is an example of where you don't use the word this, or you're at least not seeing the word this within a class. But
Is this within the
yeah. So this is the full context of this exact code segment is that it's a method within.
I'm actually going to update it right now because I just realized I should probably put a class name. So I'll just put a class name in the function
Yeah.
declaration.
Cool. Yeah. So this is if you were implementing the remove method for a linked list. This is how it would work. And so front refers to this like list front attribute that I talked about earlier, and it refers to the linked list. Good? Okay. But now, different case. For time, I'm going to just use the same diagram. If we were removing Chris, we set prev to null, cur to front. Cur is not null, so we go in. But then cur's value is name, and prev is null. So,
Sorry, I literally just updated it.
oh, that's funny. So yeah, this just means that it's a method that is in the linked list class. So we see that prev is null, and this is a special case, so we want to reset the front of the list to be Kerr's next, which is Aaron. And we do this because if we just, first of all, I can't pull that down, can I?
What's that?
I can't just like physically pull this?
No.
Conceptually, we want the front of the list to now point to Aaron because it's the new front of the list. On a code level, if we tried to go and set the previous pointer's next pointer to be the whatever the next was going to be, but previous was null because we're the head, we can't do that. All that to say, that is an example of when you would want to use a special case for the front of the list. All clear? Okay. Thanks, Chris.
No worries, sorry for the rudeness of the board.
Okay. Cool. So that's the end of the content review. My last things I wanted to say are, be sure to use the reference sheet they give you. It can be really hard to remember all of the exact syntax for, like, if you're inserting something into a vector, like, does the index go first or does the value go first? Substring, I know that works differently from Java for those of you who are familiar with Java. So look at the reference sheet really carefully, and also it can help with like handy functions like the contains method for grid and stuff. Beyond that, this is a tip that another CS lecturer at this school told me once that I found really helpful. On a separate sheet of paper or on your actual exam, I won't mind when I'm grading, just write down 3 things that matter to you in life, and those would ideally, I guess, they would be whatever you want. The reason for this is psychologically, like, if you remind yourself, like, hey, these are things that matter to me, and if those things are maybe not related to CS, or if they relate to like knowledge acquisition rather than like grades and stuff, it will like put you in a better headspace for taking the rest of the exam, and then you'll actually do better and just be happier. So, little recommendation I have. Any questions before we maybe move on to a problem or two? Yeah?
We see all people like stuff like, oh, they like bring like a book tonight and do testers that.
You are going to talk about it on Wednesday, but you're allowed to bring in pretty much anything that if you don't bring the book, you can. If you don't bring notes, you can. I mean, I wouldn't overdo it if I were you. It's not necessarily good time management to be flipping through the book in the middle of the exam.
I recently ran out of time on an exam because I was looking into my like textbook for everything I already knew how to do, and then it was bad. So I think the reference sheet is most of what you need to know. It's really handy that that is provided. Other things? Cool. So we have about 10 minutes left. Yeah? Sorry. Okay. So priorities, recursion problem or linked list problem or something else? Okay, I'm hearing both. How about, I think I heard more recursion, so why don't we do a quick recursion problem, and then I can stay after, I wouldn't mind staying after for a bit. I don't know if we would record that, but yeah, I can do whatever. And then also, I'm personally going to be working the layer from 10 to 12 tonight, which is helpful only to the people in this room, but not the people in the video. But I'm doing actually conceptual help with the layer tonight. So if you want to come by between 10 and 12, I can talk to you about this midterm. Otherwise, like, feel free to ask on Piazza, email your section leader, email lecturer head TA. And beyond that, do as many section problems as you can, and best of luck. But I'm saying that as if this is over, but I'm going to do a problem right now. OK, so let's find. Do any of you have examples of things you want to see, or I can just find something really quickly? Backtracking stuff? OK. Do you have a problem in mind from like an old midterm or a section problem, or I can just like find one? OK, let me look in. Chris, where are the old midterms?
Going down. Oh, what are you looking for? The section problems or the?
I was going to look for old midterms. Are those up?
Oh, yeah, they're all. If you go down down a bit, midterm information page right there. And keep on all the way down the bottom. There we go.
Okay, let's do number 2. And I would bet that there is one that has backtracking. Oh, they probably wouldn't say it's backtracking in the
Yeah,
thing.
keep going down. I think there is one in the, I want to say, keep going,
This might, I really should have done this before. I'm sorry.
yeah, recursive exploration is probably one that needs backtracking.
Really should have just done a section problem.
You want to do a second problem, you still can.
Okay,
I mean, all the answers are on here, so everybody can go look at the answers.
true. Okay, so yeah, let's do a problem I'm more familiar with.
Who's done the dominoes problem? That'd be a good one for people who haven't done it. Have you looked at that one? It's in one of the sections about.
Section 3.
Yeah, section 3.
It's a pretty good one. If you don't know it.
Ah, yes, I did. Ha ha ha. Proofread this one. Okay. So, domino chaining. Great. Do you want to like do this interactively or just have me run through it? I think it won't help you. Like if I just do it, it'll be like looking at the solution. So let's have some people shout some things out. This is some teaching section right now. Oh, then we probably want to board it, I'm guessing. Okay. If only I had a real eraser like this. Chris, would you mind pointing over here? Well, I really just took a chance. I thought this was, it is a chalkboard eraser, but it works for this too, which makes me happy. Should have asked also if you were good at this, but it's on the video, luckily. Oh, and I can. Is there a way I can remove the little line break there? Do y'all know how to do that? Or if I. That did not help at all. Okay. So that's fine. Yeah. Okay. I'm gonna give you all a minute to read and then just like start shouting out things you think we might need for how to do this, little key insights. Also, in case this wasn't clear for those of you at home, this is the domino problem section, handout 3, problem 7. I'm going to scroll this down a little bit because the struct is important as well. Okay, crowdsourcing. When we see a recursive problem like this, what's the first step you take for thinking about solving it? Base case, cool. What might that look like here? No dominoes left? Cool. Okay. So just like, this is going to be like a little ideas section over here. Base case. No dominoes left. We're using an E in this. Little overloaded spelling here. Some people liked that joke, others didn't. Okay. Okay. No dominoes left. Good base case. What does that mean? Like conceptually for this problem.
If I keep track of which domino we're at, then when if we keep updating it to the end, and if it reaches the end, then it will return true. So if we have a helper function that stores the position you're at currently and the end position, and if they're equal, and that means we've traversed the whole list of dominoes, then return true.
Okay.
So that you would return false otherwise somewhere along the way. And so if you reach the end without returning false, then
Awesome. So can someone just remind me really quickly like what the whole function, like returning true and returning false means? You being evicted? Yeah. Yeah. Okay. So if we reach the end, thank you. So in this function, we return true if there is a chain from the first number to the second number in our parameters, and false otherwise. So what does it mean if we run out of dominoes to check? Yeah? Awesome. So important to think about like when you're checking when you're coming up with your base cases, like what do we want to do in the base case? So if we have no dominoes left, that means no chain found. Also known as return false. Cool. Other things we need for this function. Cool. So, question for you. So, you're talking about the second number of a domino is the one we're looking for. So, what domino are you referring to?
we can pass the parameter which calls the current. So we need to know which domino we're looking at. And so there's no other, we have to keep updating that every time we recursively call the function. We can have like a current, an integer which calls this domino.
Sure. Okay. So we have, this is horrible board management, but we're going to need a helper function and like added parameter which domino we're currently looking at. Okay. Also, For those of you who had a time scheduled for tonight, it is 8:30, so I won't be offended if you get up and leave. Otherwise, I think I can probably stay till like 9, and then I have to get ready for layer. Okay, so we need in our helper function that we're going to call some way of keeping track of what domino we're currently looking at, assuming we're going to like try to look at several dominoes as like the end of our chain. So. Cool. Other things we're going to need. Okay. Unused dominoes. Other things? Could be talking about base cases, recursive cases, things we need in the helper function.
Sorry, I'm going to make your computer stop. Not
Whoa!
caffeinated.
That's amazing. So we're solving this problem of how to tell if a chain exists. What other pieces do we need before we start like writing the code for this? The last domino?
Yeah.
And so what is that going to help us with?
Like checking whether if you traverse the whole list, then you can check. That's what I was saying earlier, like you can return to if you traverse the whole list, you have to run. You can check whether, like as a base case, whether the current one is equal to the last one. That means you've gone through each one and seen whether a chain exists for each one, and then so return true.
So yeah, so the chain existing talks about like linking from, for instance, like you can link from like the 4 to the 5, 5 to the 3, right? What do we want? When do we want to return true versus false?
Like if you, so suppose for the first and second one, like 4 and 4 are the same, and then 5 and 5 are the same. The fact that you reached the third element in the list, that means you check that the list, the chain exists between the first two, and the chain exists between the second two, and so you're at the end of the list. So you would return true once you reach the third domino.
So, well,
What? That's not good.
my computer doesn't respond well to caffeine, I guess.
It's not.
So, does someone want to remind us like what the parameters? Sorry, yeah.
So usually to return true if the two numbers are found on the tile. So two numbers are found on the tile.
Yeah, so that's a key point here about what this chain exists function is supposed to do. You're seeing not only does the chain exist among all the dominoes or between each one, but can you start at one number and end at a different number specifically? Does that make sense? So given that, how might you amend what you were saying as a different base case?
So you could check with the first and the second one, right? Like part of the domino.
Mm-hmm.
But the thing is, like, suppose you only had one domino on the list.
Yeah.
Then you would return true. Like that means the current position is the last one. So you would return like that. So wouldn't that be a base case? Like not talking about which part of the domino you're looking at. Like the fact that you're at the last domino or at the only domino means that you've checked all the other dominoes.
So,
The position of it, not like the number that's on the domino.
So yeah, there are a couple of really important like pieces to how this function is going to work. The first is making sure that you can chain the dominoes. So like as you were saying, if you're able to get like from the first one to the last one, whether there are any intermediate ones, then that's important. The other important part is satisfying this condition of chaining from some number to another one. So if you only had one domino and it happened to be 6, 2, then you'd be good to go.
Yeah.
But if it's just one and anything else, in fact, you just return false immediately. Does that make sense? Okay. Cool. So what other pieces do we need to figure out either base cases or reducing the problem? Yeah?
Maybe like the
Previous domino? Okay. And what does that do for us?
I don't know, I guess it's like you want to match up, like, you want to match the numbers, right?
Mhm.
You want it, I don't know what it is, but
Yeah, no, that was good. Because you want to keep track of.
like,
Mhm.
I guess you don't need to like return the list.
True. Yeah. So, sorry, I'm not good at. I've been bad about return or like saying what's going on for the video. So we're talking about the fact that like you do need to keep track. You don't need to keep track of which dominoes led you to a specific true or false. You just need to know whether it's true or false. So what information do you need to keep passing with you through these recursive functions to know when you've either reached a case where you return true or false?
You need to update where the current end of your transmission domino.
Yeah. So we have a parameter right now for the current domino. Is that what you're suggesting, or a different thing?
Yeah.
I guess maybe which side of the domino you want.
First side or the second side. So when you're looking at like the first side or second side, what is important about the two sides?
You have a set down from the right side and then for whichever side is laid out. So it says in the problem you just flip the domino.
Yeah.
It could be either the first or the second.
Yeah.
And knowing which one it is, you can knowing which one it is.
Right. And so the domino struct has the first and second, and you can flip it so either one is either one. And so when you're making a chain, whether it's the first or the second, like what does, I guess, like the outermost, you mentioned this, what does the outermost value have to be, or what do you want it to be? That was a bad terminology. Starting over. So you're making a chain. Can you do the camera a little bit? Might have started with some diagrams that might have made this more intuitive. So, so you have your 1 and 4 and 4 and 3 and 3 and 1. And you want to chain from 1 to 1. Can you see how do you chain these dominoes so that that happens? Yep. Awesome. So we can chain 1 to 4. You have your first domino here. You chain the 4 on the as second here to the 4 who's first here, and chain second here, which is the 3, to second here, which is a 3, and end on 1. Make sense? So how are you able to tell, essentially, if you can both continue the chain, as you were saying, that's important, and whether you are, whether you finished? Because those are both two important things you need to be checking on throughout.
So I think like you don't even need to pass like the current domino that you're finishing. You only need to pass like the second number of that domino. And so then like the base case would be if the second number of that domino is the number that you're looking for, then you can just automatically like just turn to the number and like this. And then I guess you write like a for loop that would go over all the rest of the dominoes like in the list that you have left. And it would like check the first number of the domino, then flip it and check the second number of the domino. And if neither of those work, then you go on to the next one and you check all the dominoes in the list.
Awesome. Great. Lots of things there. So rather than like some parameter that is the current domino, we can convert this to what is the second number, I think you were saying, like of the last domino that you saw.
Yeah.
So so I'll say like current end of chain, which is some number. And so as a base case, check if the end of the chain is what? End of chain is num we want. And then, so we were passing the current end of the chain, and we're also passing this list of dominoes that we have left to use. And then, so how do we reduce from, let's say we didn't encounter either of these base cases. There are more dominoes, and we haven't reached the end of the chain. What does the recursive step look like? And you already gave that to us, but does someone want to recap how we reduce to the base case?
Or domino and domino, just domino first, and down four, and domino.
Yeah. So we want to look at each domino for each domino left. And then what is the, what's the condition that lets us like continue the chain? Sorry, there's some, oh, the noise is over there, so it's not showing up in the video. Haha. So you were saying if either of the like numbers in this domino is equal to the current end of chain, then what?
Then the other side of that value, so if the first of that domino matches value, then we'll do the second. Otherwise, there's
Awesome.
a record on that. I think it out of the set.
Cool. Okay, so if either num and domino is equals current end, then recurse on a second on other number. And implied in there is remove the domino from the list. Oh, I can't move that. Board management, Colin. So, do you mind if I erase this example? Otherwise, what do we do? I'm seeing a shaking head. You don't have to do anything. Exactly. Cool. So if we've gone through all the dominoes and we haven't returned true yet, then you return false. Exactly. Return false if no domino worked.
Do we have to store like whether we're looking at the first or second? Because if we have the vector of the domino stuff and we store the first and second, we just need to have three parameters: the list, the starting value, and the ending value. We don't really need any other parameters.
Exactly. Yes. So just to clarify, we need to keep track of the current unused dominoes, but we already have that in the form of the dominoes vector, which we can remove from. And the starting value and ending value, we can actually change to reflect what the new starting value is based on what the end of the tile that we didn't use in the chain was. Make sense? Cool. So that's how our recursive calls work, and then we return false at the end of the loop if we checked each recursive call and none of them returned true. Otherwise, we return true in here if we found one that worked. Make sense? Okay. Cool. Anything else you all would like to see? Hmm?
So when you say the history functions which have like pointers and references which have very different functions, so we possibly do exactly that.
I think in 10 minutes, perhaps not. But I mean,
There was one
yeah.
section 5, there was one question, like a short one, which had like pointers and references that you wanted to probably take care of.
Sure. Okay, we can look at that on the computer.
It says 10.
Yeah, no, we're good.
Is it first one?
Cool. And it would be awesome if we could see the screen and the board at the same time, although maybe.
Try to do it on, I would just do it on camera, if you kind of walk through it maybe.
Yeah, okay, cool.
That would be a little, actually, writing these things down is always a good thing.
Yeah. Let's see if we can do it verbally and.
You can try,
Yeah. Okay.
but you can't do it. I wouldn't do it verbally. Like, I would never do this in verbally. I would absolutely just write down all the
Okay.
thoughts.
Do you think there's a way I could just as someone who's not really familiar with computers, surprisingly enough, can I pull a little text box here or something? Is that possible?
I don't think it's really easy to do.
You know what I can do? Okay. I'm going to see my notes for a second. Oops. Yeah. Why? Sorry about these technical difficulties. I hope you all appreciated these series of unfortunate events references. Aaron worked really hard on them. Awesome. So down here, I'm going to keep track of local variables. I should probably All right. So in main, we see we have, I'll set Sunny equals 6. Klaus is 21, and Violet is 2. now we call VFD on, so now I'm just gonna make a little frame, a stack frame for VFD. And I have, this is not exactly, it would be easier if I could actually draw right now, but essentially like pointer to Sunny, 2, because we only care about the value, and 21. In here, we have Duncan equals pointer to Sunny, Isadora is 2, and Quigley is 21. And that's
But how long is passed by reference?
exactly 21 passed by reference. And so like passed by reference, so like passed by reference refers to which one? Klaus. So this is generally how I would go about doing a stack trace problem. So now we go into VFD, and what happens?
Isidora points to 2. So 2, Isidora is equal to 2 plus what Duncan points to.
Mm-hmm.
And Duncan points to Sunny's value, which is -6. So Isidora becomes -4.
Yes. Are there negatives here that I was missing? Probably. Oh, where did I get this from? Yeah, that's a minus that just didn't get copied over. Okay. So, yeah. So we add the dereferenced value of Duncan, which is Sunny, which is -6, up here to Isadora. So I'm going to say this goes to -4. Then Quigley times equals whatever is Isadora, which is -84. And I'm just going through like here. And then we dereference Duncan, and it's set that equal to 1. So we go up here to Sunny and change that to 1. And I should have said also we modify Klaus since that was by reference. Change that to -84. And then Isadora times equals Duncan, which at this point is,
But Isidora is equal to
oh, sorry. Yeah. Exactly. The pointers or the asterisk gets so confusing. Isadora becomes the dereferenced version, which is 1. Make sense? So now we come back up to main, and we have these variables here. And we print out 1, -84, 2. And is that what the answer says? Let's see. Awesome. Does that make sense? Yeah, if you want to ask your section leader or come to the lair at some point between now and Thursday, I think you can pretty nicely have a section leader walk you through like drawing a stack trace with the pointers and stuff, because the drawing is really crucial for keeping track of things and for getting partial credit if the person grading can like figure out what your thought process was. Make sense? Okay, so it looks like we are about out of time. Thank you so much for coming. Any last minute questions? Cool. Well, good luck on the exam, and my name is Colin.